equal, equivalent, or neither. Okay, follow this step-by-step approach. Step 1, you're going to simplify each set. So here we take away all duplicates, forget about order, we write them clean. So we have A, B, it becomes what? AB. We take away the duplicate. So we've written it clearly and cleanly in its roster form. Step 2, we are going to compare elements directly. So check, do both sets contain exactly the same element? Forget about the order. If yes, they are equal. If no, we go to step 3. Step 3, what are we doing? We are counting elements in each set. So you're going to find cardinality for A, cardinality for B. If the cardinalities are equal, then what? They are equivalent. Remember, equivalent is all about cardinality or size. If they are equal, then what? Equivalent. If they are not equal, then that means that what? The number of elements in A is not equal to the number of elements in B. And for that reason, they are neither equal set nor equivalent set. When we're done with that, we write down our conclusion clearly. We state that A equal B, or A is equivalent to B, or A and B are neither equal nor equivalent. Let's practice. Let's try some worked example. So here's the question. For each pair of sets, determine whether they are equal, equivalent, or neither. Okay, so these are the questions that we have. A, set X, Y, Z. B, X, Z, Y, X. But before we do all these things, please remember, remove all duplicate, compare and see if they're exactly the same element or same sizes. Then we conclude and make our decision that they are equal, equivalent, or neither. Let's do this. So for A, what do we see? We see X, Y, Z, right? So A, we see what? X, Y, Z. No, let me use my curly brackets. Then for B, what do we see? Z, Y, X. Yep. So it's X, X, Y, Y, Z, Z. So same element. Therefore, they are what? Equal. What about B? 1, 2, 3, 4, then A, B, C, D. So here what we are seeing is what? Numbers here, alphabets here. So they're not the same members. Then let's look at their sizes then. So size 4, size 4. So for B, we are seeing that what? Number of elements in C equals 4. And the number of elements in what? D equal 4 as well. So 4 letters here, 4 numbers here. Since the cardinalities are equal, we have what here? Equivalent. Okay? So we have equivalent. Right. Then for C, E equals cat, dog, bird. F, fish, frog, snake. Yep. Animals, animals. But not the same animals. So they're not exactly the same. So they're not equal. Let's check the size. Size of what? E. So let's bring C right here. So the size of elements in E equals what? Cat, dog, bird. So 3. And the number of elements in what? F. We have fish, frog, snake. 3 as well. So because both sizes are 3, what do we have? Equivalent. Right? Cool. Then for D, we have G equals 2, 4, 6, 8. H equals 2, 4, 8. So let's check. Same elements, 2, 4, 8, 2, 4, 8. Yes, but 6 is not here. So because 6 is not here, they are all not the same. Then size 1, 2, 3, 4. Size 1, 2, 3. Cardinalities are different, so they are not equivalent either. So here we have what? Neither. So it's neither equal nor equivalent. Very easy, right? Let's go through the solutions quickly. So in A, we realized that what? It was just the order, right, that they changed. It's X, Y, Z, X, Y, Z. So they are equal. Then here, 1, 2, 3, 4. 4 numbers, A, B, C, D, 4 alphabets. So numbers, alphabets are the same thing. So they are not equal. But because they are both 4, 4 of size is 4, 4, that's equivalent. Then here we have cat, dog, bird. 3 animals. Fish, frog, snake. 3 different animals. So now the same animals, therefore not equal. but they have the same number of animals, 3, 3. And for that, what? Equivalent. Last one, we saw that what? This is what? 2, 4, 6, 8. And here we have just 2, 4, 8. We don't see the 6 there. That means they are not equal. Then we went on to check the size. 1, 2, 3, 4, and 1, 2, 3. Sizes differ, so they are not equivalent either. So here we draw the conclusion that G and H are neither equal nor equivalent. Let's look at a deeper comparison problem. So here we have our universal set, right? Being 1 through 10. Then A is the set of all x such that x is even, but x is what? Less than or equal to 10. Same goes for B, but B is what? Odd, not even. Okay, so we are going to write our A and B in roster form. Find what? If they are equal or equivalent. Then is it possible for two sets to be equal but not equivalent? So always make sure you think before you solve. You're going to list your even and odd numbers separately, compare them, then answer some questions. Let's do this together. So you're going to write A and B in their roster form. So A in the roster form, we are just listing, right? For the universal set is 1 all the way to the 10, but A is just the even numbers with 10 inclusive, right? The equal sign here means 10 inclusive. So we have 2, 4, 6, 8, 10. Then for B, what do we have? Odd. So odd, we have 1, 3, 5, 7, and then 9. Okay. All right. So we've written them in their roster form. B is asking, are A and B equal? So equal means we have to check the elements there. I see even numbers, I see odd numbers, even though they are both numbers. But 2 is not here, 4 not here, 6 not here, 8 not here, 10 not here. Okay, so they are not equal. But are they equivalent? Are they equivalent? Let's see their sizes. So how many numbers here? 1, 2, 3, 4, 5. So we are checking, right? Let's write it down. So B. So B, we know that the number of elements in A equals 5. Then what about the number of elements in B? That's what? 1, 2, 3, 4, 5. 5 as well. What does that tell us? Since they have the same size, A and B are what? Equivalent. So you can write it down like this, or we can use the notation that what? A is equivalent to B. Okay. Then C. Is it possible for two sets to be equal but not equivalent? If they are equal, what does it mean? It means that what? The number of elements in there, they are the same. Therefore, their sizes, right, would also be the same. So if their sizes are the same, it means they are equivalent. So the answer is no. Okay. If A equals B, then they must have exactly the same number of elements. So then that means that if they are equal, they would always be what? Equivalent. Okay. So let's go through our answers together. Right. So we saw A, the roster form. We listed our elements A, listed our elements B. Then we were checking if they were equal. We saw that they didn't have the same elements, but then they had the same sizes, and that's what made them equivalent. So for C, we said what? No. No. You're asking if it's possible for two sets to be equal but not equivalent. No. If A equals B, remember, they have the same members inside. Okay? So if they have the same members inside, then if I'm counting the number of members in both, the count will end up being equal. So that will make the sizes equal. And if the sizes are equal, we call that what? Equivalent. So equal sets are always equivalent. Remember that, right? Always equivalent. So think of it this way. To be equal is a higher standard than to be equivalent. So you must also share the same element, not just the same count. First, they have the same element. Then they have the same count. So they are equal and they are equivalent. So remember, equal sets are always equivalent. All right, let's see this in real life. So in real life, yes, class list, two teachers got the same 30 students in different orders. What is that telling us? That they are equal sets. They are the same students, just that they've been ordered what? Differently. Then class sizes, Form 3A and Form 3B, each have what? 40 students. So different people, but the same count. That is what? Equivalent. Not equal. In survey responses, two groups may both have what? They may both give 4 responses each, but to different questions. So then that means what? It is equivalent, same size, but then the answers are different, not equal. Then recipe ingredients too. Two chefs may use what? Identical ingredients, but then the ingredient sets are equal, okay? And therefore they are what? Equivalent. So let's look at this scenario. Library A has what? Math, science, English, history. Library B, English, history, science, math. And library C, French, geography, music, art. Let's compare A and B. A and B, what do we see? Math, science, English, history. Math, science, English, history. So those are what? Equal. And because they are equal, what's the cardinality? 4. So 4 subjects, same subject, even though B ordered them differently. So they are equal and they are equivalent because both are what? 4 subjects, 4 subjects. What about A versus C? A, math, science, English, history. C, French, geography, music, art. Math, not here. Science, not here. English, not here. History, not here. French, not there. Geography, not there. Music, not there. Art, not there. So they are not equal, right? They are 4 subjects, all right, but they are not equal. So because they are not equal, yet they have four sizes, their sizes are equal. And because their sizes are equal, they are what? Equivalent. Okay, so that is what? Equivalent. Same cardinality of 4, but the elements are not the same. All right, so please remember, equal sets are always what? Equivalent, but equivalent sets are not what? Equal. This distinction matters, all right, for planning and resource allocation in real life. Quick check. So let's test our understanding before we say goodbye. As usual, question 1. Are PQR and RPQ equal, equivalent, or both? Let's look at it. PQR. PQR. Same elements. They've been ordered differently, so they are equal. Once they are equal, we know that what? They are of the same size. Size 3, size 3. So those are what? Equivalent. So equal and equivalent. Question 2. 1, 2, 3 and ABCD equivalent? Explain. So 1, 2, 3, ABCD, numbers, alphabet. So first we know they are not equal. Now check sizes. 3, 4. So they are different sizes. That means they are not what? Equivalent either. So here we see that what? They are not equal sets, neither are they equivalent sets. Question 3. Can 2 sets be equivalent but not equal? Give an example. So can 2 sets be equivalent but not equal? So if you have a set like 1, 2, 3, right? So say A, 1, 2, 3. And then B, A, B, C. 2 sets. Equivalent. So 1, 2, 3. 1, 2, 3. These are numbers and these are alphabets. So we know that they are not equal. But then their sizes are 3, 3. So yes, we can have 2 sets being what? Equivalent. But then what? They are not equal. That's possible. Then question 4. Remember, if A equals B, must A be equivalent to B? And if A is equivalent to B, must A equal B? So if A equals B, then we know that yes, A is equivalent to B. PQR, PQR, they are equal. And they have the same sizes, so they are equivalent. So if A equals B, then yes, A must be equivalent to B. But if A is equivalent to B, 1, 2, 3, and ABC, must A be equal to B? A, B, C, These are not the same elements, letters and numbers. Okay, so if A is equivalent to B, then A must not necessarily be what? Equal to B. Let's go through our solutions quickly. So the first one, we saw that what? PQR were the same thing, just ordered differently. So they were equal, and if they are equal, equivalent. In the second one, we saw that what? 1, 2, 3 and ABCD had different sizes. So since their sizes were not the same, they were not equivalent. Then we're asked the question of whether what? 2 sets can be equivalent but not equal. And we saw that what? These are numbers, letters, 3 numbers, 3 letters. They are equivalent. but then the elements in there, these are numbers and these are letters, they are not equal. So we saw that yes, indeed, elements, we can have two sets what having different elements, which doesn't make them equal, but they can have the same size, and that will make them what equivalent. Then question 4, if A equals B, then yes, A must be equivalent to B. But if A is equivalent to B, doesn't necessarily mean what A would equal B. All right. So my people, common mistakes to avoid. Please don't confuse equal with equivalent. Remember, equal means they have the same element. Equivalent just means what? They have the same size. Okay. Then if you don't say equivalent size and equivalent sets are equal. Remember, it is the equal set that can be equivalent. If you are equivalent, you have the same size. It doesn't mean that your elements inside the set will be the same. Then forgetting to simplify before you compare. Always simplify. Do away with duplicate. Okay, so 1, 2, 2, 3. You have a duplicate here. Simplify it to 1, 2, 3 before you start comparing. Then please, equal sets are always equivalent. Equivalent sets are not always equal. Always remember this. This is very, very, very important. So this is your problem solving checklist. Make sure that when you're comparing two sets, you are following these steps. You simplify each set, do away with all duplicates, compare them, check if they have exactly the same members. If yes, then they are equal. If they are equal, they are equivalent. If you compare the members and they don't have exactly the same element, then check their sizes. Are the sizes the same? If the sizes are the same, we write what? That they are equivalent. If the sizes are not the same, then they are neither equal nor equivalent. So let's lock in. What have we learned in this lesson? We have seen equal sets, exactly the same elements in both. We've seen equivalent sets. They may not have the same element, but they have the same size. So remember, equal sets are always equivalent. But equivalent sets are not what? Equal. Remember this